Assalamualaikum everyone and a very good day to all. In this video, we shall learn about the 5 layers of TCP/IP protocol suite and how the packets in each layers are named and also the addressing mechanism used. Each layer of this protocol suite will be further explained in the several chapters to come. Okay, this second part of this second chapter is just an introduction and also preparation for the rest of the course. Here is the table of contents for you to navigate through this video. Okay, so what is TCP/IP? It stands for Transmission Control Protocol, Internet Protocol, and it is a protocol suite, which is a set of protocols organized in different layers, and this protocol is used in the internet today. Okay, so TCP/IP is a hierarchical protocol which is made up of interactive modules. Remember modularity in previous video, and each of which provides a specific functionality. Okay, so what does hierarchical means? It means that each upper level protocol is supported by the services provided by one or more lower level protocols. Okay, as you can see in the next figure, here is the layer 1 of okay, on the right is the current TCP/IP, but on the left is the original TCP/IP. Okay, originally TCP/IP protocol suite was defined as 4 software layers. Okay, and these software layers are built upon the hardware. So 4 software layers, and then on top at the bottom we have the hardware. But today, however, TCP/IP is taught as a 5-layer model. So the hardware devices are considered as a layer, and it is and the 5 layers from layer 1 are the physical, data link, network, transport, and application layers for layer 5. Okay, so a little assignment for you today after you finish this video to create a mnemonic phrase out of the first letter of each of this layer, and let's standardize by starting from layer 1. Okay, so let's start from layer 1 instead of layer 5, and then write them in the comment down below. Okay, for example, please for physical, and then perhaps deliver for data link, news for network, to for transport, and agent for application. So please deliver news to agent is my example of mnemonic. Okay, now we are going to see how the layers in the TCP/IP protocol suite and in this particular example, they are involved in communication between 2 hosts, in this case A and B. Let's assume that we want to use the suite in a small internet made up of 3 LANs or links, each with a link layer switch. And then we also assume that the links are connected by one router. Let us assume that computer A communicates with computer B. As the figure shows, we have 5 communicating devices in this communication. We have source host or computer A, the link layer switch in link 1, and then we have router, and then we also have the link layer switch in link 2, and the destination host, i.e. the computer B. And each device is involved with a set of layers depending on the role of the device in the internet. Okay, the 2 hosts are involved in all 5 layers. The source host needs to create a message in the application layer and set it down the layers so that it is physically sent to the destination host. Okay, so the destination host needs to receive the communication at the physical layer and then deliver it through the other layer to the application layer. Alright, the router is involved in only 3 layers. Okay, so there is no transport or application layer in a router as long as the router is used only for routing. Although a router is always involved in one network layer, layer 3, it is involved in n number of combinations of link and physical layers, in which n is the number of links the router is connected to. The reason is Each link may use its own data link or physical protocol. For example, in the figure below, we can see the router is involved in 3 links, link 1, 2, and 3, but the message sent from source A to destination B is involved in 2 links only. Okay, each link may be using different link layer and physical layer protocols. So this is why the router needs to receive a packet from link 1 based on one pair of protocols and deliver it to link 2 based on another pair of protocols. Okay, a link layer switch in a link, okay, however, is involved only in 2 layers, which are data link and physical layers. Although each switch in the figure has 2 different connections, the connections are in the same link, which uses only one set of protocols. This means that unlike a router, a link layer switch is involved only in one data link and one physical layer. Now let's discuss the functions and duties of layers in the TCP/IP protocol suite. To better understand the duties of each layer, we need to think about the logical connections between layers. Okay, let's use the same connection as before. And the top figure shows the logical connections in our simple internet. Okay, so using logical connection makes it easier for us to think about the duty of each layer. As the figure shows, the duty of the application, transport, and network layer is end-to-end. However, the duty of the data link and the physical layer is hop-to-hop, in which a hop is a host or router. In other words, the domain of duty of the top 3 layers is the internet, and the domain of duty of the 2 lower layers is the link. Next, let's look at this figure, which shows the second principle discussed previously for protocol layering. We show the identical objects for each layer related to each device. Note that although the logical connection at the network layer is between 2 hosts, like I shown you in the previous slide in this video, we can only say that identical objects exist between 2 hops in this case, because a router may fragment the packet at the network layer and send more packets than received. So it will not be identical. So in this case, it will be identical between 2 hops. Note that the link between 2 hops does not change the object. It will be identical objects. After understanding the concept of logical communication, now we are ready to briefly discuss the duty of each layer. Okay, so just briefly, in physical layer, we can say that the physical layer is responsible for carrying individual bits in a frame across the link. Although the physical layer is the lowest level or lowest layer in the TCP/IP protocol suite, the communication between the 2 devices at the physical layer is still a logical communication, because there is another hidden layer, which is the transmission media, under the physical layer. Okay, so the 2 devices are connected by a transmission medium. And this transmission medium could be either a cable or air in terms of wireless. And you also need to know that the transmission medium does not carry bits. It actually carries electrical or optical signals. And so the bits received in a frame from the data link layer are transformed and sent through the transmission media. But we can think that the logical unit between 2 physical layers in 2 devices is a bit. And there are several protocols that transform a bit to signal. Okay, let's go to the next layer, data link layer. We have seen that an internet is made up of several links, either LANs and WANs connected by routers. There may be several overlapping sets of links that a datagram can travel from the host to the destination. So the routers are responsible for choosing the best links. Okay, so remember, there is overlapping, there is redundant route that they can choose, but the router are responsible for choosing the best links. However, when the next link to travel is determined by the router, the data link layer is responsible for taking the datagram and moving it across the link. Okay, so the link can be wired LAN with a link layer switch, a wireless LAN, or a wired one or a wireless one. We can also have different protocols using with any link type. In each case, the data link layer is responsible for moving the packet through the link. Okay. TCP/IP does not define any specific protocol for the data link layer. It supports all the standard and proprietary protocols. Any protocol that can take the datagram and carry it through the link suffices for the network layer. The data link layer takes a datagram and encapsulates it in a packet called a frame. And each link layer protocol may provide a different service. It could be provide complete error detection and correction, or some might provide only error correction. Next, let's go to the next layer. We have network layer. Network layer is responsible for creating a connection between the source computer and the destination computer. The communication at the network layer is host to host. However, since there can be several routers from the source to the destination, the routers in the path are responsible for choosing the best route for each packet. We can say that the network layer is responsible for host to host communication and routing the packet through possible routes. Again, you may ask, why do we need the network layer? We could have added the routing duty to the transport layer and dropped this layer. Again, from previous video, one reason is the separation of different tasks between different layers. Okay, and the second reason is that the routers do not need the application and the transport layers. So separating the tasks allows us to use fewer protocols on the routers. Network layer also include unicast and multicast routing protocols. And one of the protocol in network layer is main protocol, internet protocol, which is IP. And they define the format of the packet called a datagram at the network layer. Internet protocol also defines the format and the structure of addresses, also responsible for routing a packet from its source to its destination, which is achieved by each router forwarding the datagram to the next router in its path. Next, let's go to the transport layer. Transport layer, okay, in previous slide, in this video, you can see that the logical connection at the transport layer is also end-to-end. The transport layer at the source host gets the message from the application layer, encapsulates it in a transport layer packet called a segment or a user datagram in different protocols, okay, and sends it through the logical or imaginary connection to the transport layer at the destination host. In other words, the transport layer is responsible for giving services to the application layer. To get a message from an application program running to the source host and deliver it to the corresponding application program on the destination host. Again, we can ask, why do we need this? Because we already have end-to-end application layer. We want to separate the tasks and duties as we discussed earlier. The transport layer should be independent of the application layer. In addition, we will see that we have more than one protocol in the transport layer, which means that each application program can use the protocol that best matches its requirement. Okay, there are a few transport layer protocols in the internet, and each designed for some specific task. The main protocol, Transmission Control Protocol, or TCP, is a connection-oriented protocol that first establishes a logical connection between transport layers at two hosts before transferring data. This creates a logical pipe between two TCPs for transferring a stream of bytes. TCP provides flow control which means that matching the sending data rate of the source host with the receiving data rate of the destination host, and to prevent overwhelming the destination. And it can also provide error control, which is to guarantee that the segments arrive at the destination without error, and resending the corrupted ones. And also can provide congestion control, which is to reduce the loss of segments due to congestion in the network. Okay, for application layer, again, in the logical connection figure, previously we can see that the two application layers is end-to-end. The two application layers basically exchange messages between each other as though there were a bridge between the two layers. However, we should know that the communication is done through all the layers. And our communication at the application layer is between two processes, meaning that two programs running at this layer. To communicate, a process sends a request to the other process and receives a response. Process-to-process communication is the duty of the application layer. The application layer is in the internet includes many predefined protocols. Okay, but a user can also create a pair of processes to be run at the two hosts. Some of them are the Hypertext Transfer Protocol, HTTP, which is basically very important for accessing the World Wide Web. And we also have the Simple Mail Transfer Protocol, SMTP. This is the main protocol used in electronic mail or email service. We also have File Transfer Protocol. This is used for transferring the files from one host to another. Okay, there are many other protocols such as Telnet, SSH, SNMP, which is the Simple Network Management Protocol, and many others. Okay. One of the important concepts in protocol layering in the internet is encapsulation and decapsulation. What does encapsulation means is basically adding header and trailer to the data, and de-encapsulation or decapsulation meaning that it removes the header and trailer from the data. One of the important concepts in protocol layering in the internet is encapsulation and decapsulation. This figure shows this concept for the small internet that we've used as an example before. We have not shown the layers for the link layer switches because no encapsulation or decapsulation occurs in this device. So in this figure, we show the encapsulation in the source host, decapsulation in the destination host, and encapsulation and decapsulation in the router. Okay, at the source host, we can only have encapsulation. We can go from application layer. We can see that the data to be exchanged is referred to as a message. A message normally does not contain any header or trailer, but if it does, we refer to it as the message. The message is passed to the transport layer, and then the transport layer takes the message as the payload, then load the load that the transport should take care of. It adds the transport layer header to the payload, which contains the identifiers of the source and destination application programs that want to communicate, plus some more information that is needed for the end-to-end delivery of the message, such as information needed for flow error control or congestion control. And the result is the transport layer packet, which is called the segment in TCP, and the user datagram in UDP, and the transport layer then passes the packet to the network layer. The network layer takes the transport layer packet as data or payload and adds its own header to the payload. The header contains the addresses of the source and destination hosts and some more information used for error checking of the header, fragmentation information, and so on. So the result is the network layer packet called a datagram. The network layer then passes the packet to the data link layer. Okay, the data link layer takes the network layer packet as data or payload and adds its own header, which contains the link layer addresses of the host or the next hop, the router, and the result is the link layer packet, which is called a frame. The frame is passed to the physical layer for transmission. And then we go to the router, we need to decapsulate and encapsulate. Okay, so once the packet arrive, or the frame, okay, arrive at the router, and then after the bits sent, this layer decapsulates the datagram from the frame and passes it to the network layer. The network layer only inspects the source and destination address in the datagram header, and then it will consult its forwarding table, okay, to find the next hop to which the datagram is to be delivered. Okay, the content of the datagram should not change by the network layer in the router unless there is need to fragment the datagram if it's too big to be passed through the next link. The datagram is then passed to the data link layer of the next link. Okay, so the data link layer of the next link encapsulates the datagram in a frame and passes to the physical layer for transmission. And then at the host, a destination host, we will only decapsulate. Okay, so at the destination host, each layer only decapsulates the packet received, removes the payload, and delivers the payload to the next higher layer protocol until the message reaches to the application layer. It is necessary to say that decapsulation in the host involves error checking as well. Another concept related to protocol layering in the internet that is worth mentioning is addressing. Okay, as we have discussed before, we have logical communication between pairs of layers in this model, and any communication that involves two parties needs two addresses. That is the source address and destination address. Although it looks as if we need 5 pairs of addresses, one pair per layer, but we actually normally have only 4 because the physical layer we don't does not need addresses, because the unit of data exchange at the physical layer is a bit, which definitely cannot have an address. Okay, this figure shows the addressing at each layer, and okay, there's a relationship between the layer, the address used in that layer, and the packet name at that layer. Okay, at the application layer, we normally use names to define the site that provides services, such as email or email address. Okay, and the transport layer, addresses are called port numbers. Okay, so this define the application layer programs at the source and destination. Port numbers are local addresses that distinguish between several programs running at the same time. At the network layer, the addresses are global, with the whole internet as the scope, and network layer address uniquely defines the connection of a device to the internet. The link layer addresses, sometimes called MAC addresses, are locally defined addresses. Each of these defines a specific host or router in the network. Okay, let's go to the next slide. Okay, the last concept that we're going to see on this protocol layering is multiplexing and demultiplexing. As you can see here, multiplexing is at the source, okay, and demultiplexing at the destination. Since TCP/IP protocol suite uses several protocols at some layers, so this is the generalization. Okay, multiplexing in this particular case means that a protocol at a layer can encapsulate a packet from several higher layer protocols. And demultiplexing means that protocol can decapsulate and deliver a packet to several higher layer protocols. In this figure, you can see that the concept of multiplexing and demultiplexing at the 3 upper layers, the application, the transport, and the network layers. And to be able to multiplex and demultiplex, a protocol needs to have a field in its header to identify which protocol the encapsulated packets belong. For example, at the transport layer, it could be either UDP or TCP, and they can accept a message from several application layer protocols. At the network layer, IP, Internet Protocol, can accept a segment from TCP or user datagram from UDP. IP also can accept a packet from other protocols such as ICMP, IGMP, and so on. Okay, at the data link layer, a frame may carry the payload coming from Internet Protocol or other protocols such as ARP. Before I end this video, please let me know how is your understanding on this topic throughout this video so far at this link. Your participation is highly appreciated. If you have any questions or comments, please let me know. Thank you and see you on the next video.